Right, welcome to Slice 5. Now I've had to step away from the light board for this one, mainly because I wouldn't have been able to do this just by drawing it all. I'm going to introduce you over this next few minutes to the way that platelets kind of go about their business. In other words, how it is that they bind to the cell membrane in order to actually get that clot done. Okay, so this is what you're looking at on screen is a diagram of a platelet, and what you can see there on screen, these things, all here, okay, all of those things, these are the platelet glycoproteins. So glycoprotein, and you can see, actually, remember I said in the previous video that we used to say GP, so GP2, but now we call them G2B, 3A, you can see that one there. So I always think this is a really good way of thinking about this is to just kind of imagine this platelet as being like a big blob of blue tack, and that these things are Lego pieces that are stuck in that blue tack. And then other platelets, and you can see that this here is another platelet, they're going to go ahead and bind together. So a way of thinking about it might be that we've got our endothelium like this, and then we get the bit in the middle that's been broken. We're exposing the subendothelial collagen, and we get the von Willebrand factor sticking out, and then we get the platelets that are kind of holding on to it like this. And remember I said I was going to draw these little hands as platelet glycoproteins? Well, there they are. And then you can see, if we're drawing this over here, we've got two platelets holding hands like that, and you can see that the thing that is going to be holding them together, there and there, is a molecule called fibrinogen. Now the problem with fibrinogen is that it's soluble. So we want that fibrinogen to be cleaved, okay, to open up its active sites, and that is to turn it from being fibrinogen into fibrin, because fibrin is insoluble. So let's just bring this back across and hone in a little bit better on what we now want to talk about. Just get rid of this, like that. Okay, first things first. We're going to look at this thing here, glycoprotein 1b. Okay, glycoprotein 1b. We got to remember a few things about what these bind to. So it's going to bind directly, as you can see right there, to von Willebrand factor. So glycoprotein 1b binds to, I'll do it like that, just a little arrow, binds to von Willebrand factor, and there's an added detail that we can actually put in on here, and that is where on the von Willebrand factor does it bind. And it binds, if we remember, on the A1 domain. The other one that we've got to think about is this one here, glycoprotein 2b3a. And this shouldn't be too much of a shock. 2b3a, that. because we've just talked about it. What does it do? There it is. It binds platelets to other platelets. Okay. Whoa, hang on. Let's change my pen back. Platelet to platelet. Right. Now, we've got another one that we're not showing on this diagram, so we're going to have to draw it in. Like this. Okay. And I'm going to draw it, and you can kind of see that it looks like an A, the way I've drawn it. And just do it like that. That's glycoprotein 1A. Okay. Now, you sometimes see this written as glycoprotein 1A, 2A. Okay. Now, what this does, and this is the reason I'm going to talk about it now, is it's going to take a platelet and it's going to bind it directly to collagen. Okay, so 3 key glycoproteins that you need to remember. Glycoprotein 1b is going to bind von Willebrand factor to the A1 domain. So it's going to, glycoprotein 1b is going to bind a platelet to the A1 domain of von Willebrand factor. Glycoprotein 2b3a is going to be binding a platelet to another platelet. And then, finally, glycoprotein 1a, 2a is going to bind a platelet to a collagen. Okay. I suppose the next question would be, well, why is all this important? So if we just move this up here a second, make it a little bit smaller, pop it into the corner. The reason that all of this is important is because we're talking about something called, the overall arching thing of what we're talking about is called tethering. Okay, tethering. So what that refers to is how do we bind the platelet to the subendothelium? Right, that's basically what we're asking. So you can broadly break this down into 2 states. Okay, let's just make this a little bit smaller again so I got some space. Okay, so state 1 is going to be, and don't forget we're talking about platelets, so if you remember back to the previous slice, we said that one of the things that takes a platelet from being, we drew it like this, from its resting to its active, one of the things, or the big thing that's going to do that, and we said is going to be shear stress. Now, shear stress, as we've said, kind of activates platelets and really gets them working. But there's another side to this coin. So state 1 is a low shear environment. State 2 is high shear environment. All right. Now, what happens in your low shear environment, if you just move this up here like this, so we're just talking about this now, we can concentrate on it a little bit better. In the low shear environment, what you're going to find is that you're going to get, and so we're talking about in trauma now. Okay, so this is, if we've got trauma of a low shear environment, what we get is direct binding platelets. It's going to remind me that is platelets. To collagen. Okay. In a high shear environment, we get indirect binding of platelets to collagen. So why might that be? Well, it's mainly because of where these environments are. So if we just focus in on the low shear environment first, the low shear environment, and we'll do this like this, for example, you tend to find the low shear environment being where blood flow pressure is low. So where might blood flow pressure be low? This is the venous circulation. Okay, so in venous circulation, where the pressure is low, if blood pressure is low, the flow rate is lower, the platelet has time to bind directly to the collagen. So what we get is platelets, so we'll do this PT for platelet. Platelets use predominantly glycoprotein 1A, 2A, and they will bind directly to collagen. Okay. Now, in higher shear environments, these are going to be represented, or representative, I should say, of arteries, arterioles, and even capillaries. Okay. Predominantly more to the arterial side of the capillary, but still capillaries. What we get here is indirect binding, as we've said. What we get with indirect binding is interaction with von Willebrand factor. Okay, and if we've got von Willebrand factor, it's going to be glycoprotein 1B, and it's going to be then everything that we've said above. Okay, so the A1 domain of the von Willebrand factor, that is our indirect, and the platelet to collagen is going to be our direct, and that brings together those two different environments that we were just talking about, the low shear environment, the high shear environment, in other words, the venous circulation versus the arterial circulation. So let's look at state 2 in a little bit more detail. So here, and then that's not the picture I want. This is the picture I want. Okay, so we're going to have a little look at this indirect binding. Okay, so there's a couple of key concepts. We need to remember that what we're dealing with is a damaged vessel. Okay, so we can see this area of damage there. Now, what we've already talked about is the fact that in the subendothelium and the endothelial cells themselves, so those Weber Palade bodies are going to start releasing von Willebrand factor. And the von Willebrand factor is going to tether itself into the collagen. And we've already talked about how it does that in the previous slices. So if you're unsure of it, what you need to do is then go back. I introduced you also during the previous slices to the concept that the von Willebrand factors kind of unfurl like a wacky waving inflatable arm flailing tube man. And this is kind of what it looks like. So you can see this is from a very nice paper by Schneider et al. And it was released in 2007. I will put a link to this for you in the learning materials section of UniLearn. But what you can see is this is the von Willebrand factor. If I can actually make my thing work. This is the, okay, we'll have to draw. This is the von Willebrand factor there, and you can see that this is below critical shear. So in other words, below a critical flow rate. As the flow rate starts to increase, as we move there, and it gets to above the critical shear, you can see that the von Willebrand factor unfurls, like that wacky waving inflatable arm flailing tube man that we were talking about. Now, what we've now got, and let's see if we can just tidy this up a little bit, like that, and let's just take that out of the picture. What you can see that we've now got is all of this. Okay, we've got our von Willebrand factor tethered into the subendothelial collagen. We've got a platelet that is attached to it. You can see that because we've got platelet interaction with von Willebrand factor, we've got glycoprotein 1b attaching to the von Willebrand factor, and then we've got the 2b3a complex there with the fibrinogen, and it's all holding together. So this is kind of the first step, really, of getting everything in shape so that we can actually form a clot. So what you need to remember is that von Willebrand factor, when it enters into the circulation, okay, becomes immobilized. So it's immobilized on the collagen. Then, that's point one, and then platelets get tethered. Okay, so they're the two key steps in this. Once the platelets become tethered, they then start to become activated. So I'm going to leave that here for now, and then the next slice that we're going to do is looking at platelet tethering and all the steps that happen in order to get a platelet locked down onto the collagen so that we can then get into how blood actually clots, in other words, the coagulation cascade. And we'll do that next.